Imagine the entire observable universe as a single city at night. Every star a window lit up, every galaxy a tower of light. Now imagine one street lamp that, for a split second, blazes brighter than the whole city and then goes dark. That is the scale of power we are hunting. The question sounds simple, but it bites hard. What is the most powerful thing in the universe? Black holes colliding, gamma-ray bursts, quasars that outshine galaxies, magnetars that tear space with magnetic storms, dark energy that stretches space itself. Power, in physics, is energy divided by time. A campfire has energy, a lightning bolt has power, so a fair search needs 3 scorecards. First, peak instantaneous power, the biggest spike nature can throw. Second, sustained luminosity, who can keep the lights on at the highest level for the longest time. Third, power density, how much howl you can pack into the smallest space. With those rules, we can stage a tournament without talking past ourselves. If we start with the fastest punch the universe throws, we crash into colliding black holes. 2 dark giants orbit, spiral, and merge, and in their last heartbeat, the fabric of spacetime rings like a bell. The power carried by gravitational waves in that instant can exceed the combined light of every star in the observable universe. For a flicker of a moment, more power pours through the cosmos as ripples in spacetime than as photons. You do not see it with your eyes, you feel it as the universe itself flexes. Before we hand out trophies, another contender slams in the cosmic blowtorch known as a gamma-ray burst. When a massive star's core collapses to a black hole, or when 2 neutron stars crash, a narrow jet drills out at nearly light speed. For seconds or minutes, its electromagnetic power can rival a whole galaxy. Because the jet is beamed, it can look even brighter from our line of sight, condensing power into a razor-thin spotlight. Get too close to that spotlight and molecules lose their grip. Quasars are a different kind of monster. They are not a punch, they are a furnace that never quits. At the heart of a young galaxy, a supermassive black hole feeds. Gas swirls inward, heats to white-hot plasma, and radiates with the light of trillions of suns. Magnetic fields can launch jets longer than galaxies, dumping energy into intergalactic space for millions of years. If the game is sustained, relentless power, the kind that sculpts galaxies, quasars, are impossible to ignore. Then there are magnetars, the cracked diamonds of the cosmos. A magnetar is a neutron star with a magnetic field up to 1,000 trillion times stronger than a fridge magnet. When that contorted field snaps, a giant flare erupts. For a heartbeat, the intensity near the source is volcanic, and the power density, the amount of fury per cubic meter, goes off the charts. Magnetars remind us that powerful can mean concentrated, not just bright at a distance. And looming over everything is dark energy, the quiet pressure that accelerates cosmic expansion. It is not a beam, or a blast, or a flare, but on the largest scales, its influence dominates the story. If we define power as the ability to do work on the universe to change its motion, then dark energy is the slow monarch, moving everything not by shouting, but by never stopping. It wins by patience. So which one is most powerful? The only honest answer is, tell me your timescale, your channel, and your yardstick. Instantaneous spike, black hole mergers look unbeatable. Long haul luminosity, quasars and their jetting cousins, blazars, sit on the throne. Power density, magnetars and neutron star smash-ups flex with energies packed into city-sized volumes. Cosmic influence over billions of years. Dark energy and gravity themselves bend the bracket. The universe is not a single contest, it is a league with different champions. But this is more than a scoreboard. It is the story of how nature moves energy around. Gravity gathers clouds, clouds light stars, stars forge elements, and when they die, they hand their energy to remnants, white dwarfs, neutron stars, and black holes. Those remnants collide, launch jets, and stir the gas that makes new stars. Power is the courier between the invisible math and the visible sky. It built the iron in your blood and the calcium in your bones. It is why there are planets to stand on and skies worth looking up at. Here is how we will travel. We will start with the spike. What it means, in numbers you can feel, for spacetime to radiate more power than all starlight at once. We will shrink those figures to earthly terms. Every power plant, every bolt of lightning, every rocket engine, all firing together and then multiply until the scale lands in your gut. We will then turn to the brightest electromagnetic flash a human instrument can catch and ask why gamma-ray bursts shine so violently. After that, we will slow the clock and watch quasars carve galaxies. Along the way, we will keep the rules tight and the language plain. No jargon that does not earn its keep. When we say 10 to the 49th watts, we will translate. When we say 1,000,000,000,000 suns, we will anchor it to the night sky, you know. When we say most powerful, we will say whose game we are playing. At the end, we will crown a winner, but only after we have earned it. Because the most powerful thing in the universe is not just an object or an event. It is the way the cosmos writes with energy and time. Sometimes it whispers for eons, sometimes it shouts, always it leaves a mark. Start with the spike you can feel in your bones. 2 black holes, each dozens of times the sun's mass, orbit so fast their paths blur. Every lap bleeds energy, the way a skater slows when arms uncross. The dance tightens, the rhythm quickens, and then the final plunge arrives. In a 1/10 of a second, the pair become one, and the universe rings. What rings is space-time. In Einstein's picture, gravity is geometry, not a tug. Accelerating masses stir that geometry and send ripples outward, gravitational waves. They do not glow like light. They stretch and squeeze the very stage that light crosses. A wave passing through you makes the distance between your shoulders and your spine alternately longer and shorter by less than a proton over a kilometer. That is the scale, and still the effect can carry unimaginable power. We know because we've heard it. In 2015, the first confirmed signal reached Earth after traveling for more than 1 billion years. It sounded like a quick chirp, rising in pitch and fading, because the orbit sped up until merger, and the newborn black hole settled. Hidden in that chirp was a staggering figure. At peak, the power carried by the gravitational waves was roughly 10 to the 49th watts. Translation: our sun shines at about 4 times 10 to the 26 watts. For an instant, the wave power exceeded the combined light of the observable universe by roughly an order of magnitude. It is not a flash you could see, it is a surge in the fabric that everything else rides on. Another way to feel it is with energy. In the last blink before coalescence, about 3 suns worth of mass turned into gravitational waves. E equals mc squared is not poetry, it is accounting. Multiply 3 solar masses by the speed of light squared, and you get an energy bill so large that every power plant on Earth, running non-stop for longer than the age of the universe, would not cover even a fraction of a second of that outburst. Human scales do not reach this neighborhood. If you could hang nearby, setting aside the small problem that tidal forces would stretch you into a string of atoms, you would not see a flash. You would surf a swell in the structure of reality. The wave would pass through you, through planets and stars, with almost no scattering, because space-time is the medium and everything is made of space-time. Gravitational waves are powerful precisely because they are terrible at interacting. They carry their news cleanly across the cosmos. Zoom into the mechanics. Imagine the last dozen orbits, the holes, each the size of a city but with masses that could swallow a star, race at a significant fraction of light speed. The unevenness in how their mass is arranged, their quadrupole moment changes violently, launching waves. When the single remnant forms, it is born lopsided. Like a struck bell, it quivers, radiating away its lumps as a ring-down tone. That tone is not sound, but it has a pitch that depends on mass and spin. From the pitch, and how fast it damps, You can read off the remnant's properties the way you can identify a glass by its note. Detectors such as LIGO and Virgo do something almost absurd to touch these waves. They send laser beams down vacuum tunnels 4 kilometers long and bounce them between mirrors polished to atomic smoothness. When a wave stretches one arm and squeezes the other by less than the width of a proton, the returning light interferes differently, and a tiny beat appears in a photodiode. The instruments are so sensitive that the rumble of trucks, a small earthquake on the other side of the world, even quantum shot noise in the laser light can swamp the signal. So teams quiet the ground, isolate the mirrors, squeeze the light to reduce quantum jitter, and teach algorithms to tell real chirps from noise. Why call this the most powerful event? Because power means energy per time, and nothing we know dumps energy faster. Quasars rule the long game. Gamma-ray bursts win brightest electromagnetic flash. But if you ask for the tallest spike on the power graph, black hole mergers sit at the top. They convert mass to energy with brutal efficiency, and do it in milliseconds. The universe does not hold that note for long, but while it lasts, everything else is background. This spike also redraws our map of the invisible. Before gravitational wave astronomy, we inferred black holes indirectly by stars that looped them, by disks that shone while falling in, by jets that screamed from their poles. Now we have a direct line to the engine room. Each detection adds a dot on a chart of masses, spins, and distances. It tells us how massive stars die, how often they pair up, whether partners were born together or met later in crowded clusters, and whether exotic possibilities like primordial black holes fit the data or fall away. The power of a single chirp becomes a census of the dark. There is a human scale to this too. A single observing run records countless blips that are not from the cosmos at all. Teams learn to tame thermal noise, seismic noise, and quantum noise. They swap heavier mirrors, refine suspensions, improve vacuum, and upgrade lasers. With the next generation, longer tunnels on Earth and detectors in space, we will hear farther and fainter. What began as one chirp will become a catalog, then a symphony, then a background hum from the whole universe. So, if our tournament has a category called instantaneous, we have a champion. 2 black holes collide, spacetime rings, and for a sliver of a second, the universe pours out more power than all its stars combined. Keep that picture in mind, because next we turn the dial from waves in gravity to the fiercest beam of light nature can muster. When the core of a dying star drills a jet clean through itself, the cosmos points a flashlight so intense it can scorch a galaxy. That is where we go next. Aim your attention at the fiercest beam of light nature makes. A gamma-ray burst is not merely bright, it is weaponized brightness, focused, sharpened, and fired from a dying star or a crashing pair of neutron stars. For a few seconds, the jet can outshine its entire host galaxy. If the beam lines up with Earth, our instruments register a spike that looks unreal, a wall of photons rising in milliseconds. There are 2 main families. Long bursts, lasting more than 2 seconds, are tied to the collapse of a massive star. The core fails, a black hole forms, and magnetic fields whip in falling plasma into twin jets that punch through the star's outer layers. Short bursts, under 2 seconds, come from mergers of neutron stars, the city-sized solar mass cores left behind by supernovae. Both families launch ultra-relativistic jets that squeeze their light into a narrow cone. The numbers explain why GRBs belong in a most powerful conversation. The sun shines at roughly 4 times 10 to the 26 watts. A bright burst's isotropic equivalent luminosity can reach 10 to the 52nd ergs per second, about 10 to the 45th watts, and occasionally higher. That is around 19 zeros more than the Sunday. Because the emission is beamed into a cone only a few degrees wide, the power aimed at us can look even more extreme. Speed drives everything. Physicists capture it with the Lorentz factor, which can be 100, 300, even 1,000 in GRB jets. At those speeds, Clocks on the jet run slow relative to us, and radiation piles into the forward cone. Alignment determines whether we see a universe-shaking blaze or silence. Inside the jet, energy turns into light by a couple of leading ideas. In one, shells of plasma, fired at slightly different speeds, slam together and make internal shocks. In another, magnetic fields twisted like rubber bands snap and reconnect, flinging particles to staggering energies. Either way, electrons spiral in magnetic fields and radiate high-energy photons. That first, hard flash is the prompt emission. Then comes the afterglow, as the jet plows into interstellar gas and decelerates. The spectrum then slides from X-rays to radio as the shock cools and expands. Some bursts have been so bright they triggered detectors through the sides of the instruments. Their afterglows have guided telescopes to faint host galaxies halfway across the observable universe. In short, bursts from neutron star mergers, we have also watched a kilonova bloom, blue light early, red light later, powered by the radioactive decay of heavy elements freshly forged in neutron-rich debris. That is not mere fireworks. It is metallurgy on a cosmic scale, the likely birthplace of much of the gold in the cosmos. GRBs reveal engines we cannot see directly. A newborn black hole or a hypermagnetized neutron star feeds from a hot accretion disk just hundreds of kilometers wide. Magnetic fields thread the disk like steel cables. Rotation twists those cables into a helix and launches energy upward in two opposite jets. Some models add neutrinos, ghostly particles streaming from the core to help clear paths along the poles so the jets can drill through surrounding matter. The afterglow is more than a pretty fade. It is a measuring stick. How quickly the brightness drops tells you the jet's opening angle. A sudden steepening the jet break means the cone has widened and we are beginning to see its edge. The color of the afterglow reveals the density of the surrounding gas and the strength of the magnetic fields. With careful modeling, astronomers back out the total energy budget, the geometry of the beam, and how efficiently gravity's fall was converted into light. For all their ferocity, GRBs are selective. Miss the beam, and you may never know the event occurred. Even aligned bursts can be dimmed by dust in their host galaxy. And while their instantaneous electromagnetic power is titanic, they do not dethrone colliding black holes on the raw peak power chart. The difference is the channel. Black hole mergers dump energy into gravitational waves that barely interact with matter, and therefore keep their power spike intact. GRBs radiate in light, which scatters and can be absorbed. Could a nearby GRB harm Earth? If one went off within a few thousand light-years aimed straight at us, the upper atmosphere would take a hit, molecules would ionize, and the chemistry that shields life could be rattled. Fortunately, space is huge, the beams are narrow, and the blowtorch rarely points at the same spot twice. Catching GRBs is a relay. Wide-field satellites NASA's Swift and Fermi, ESA's Integral, and others watch the sky and broadcast instant alerts. Ground telescopes swing within minutes to measure distance and watch the afterglow evolve. The faster that chain reacts, the more of the physics we recover from the first seconds when the engine is hottest. In our tournament terms, if the bracket has a category called brightest electromagnetic flash, gamma-ray bursts keep the trophy. They win on peak luminosity among things that shine. They win on concentration, and in neutron star cases, they double as factories for heavy elements. They do not last long, but they leave fossils, satellite logs of gamma-ray spikes, catalogs of optical afterglows, and the periodic table's richest entries stamped into their debris. Open puzzles remain. How does the jet turn bulk motion into photons so efficiently? Why do some long bursts arrive with a bright supernova, while others hide it? How strong and ordered are the magnetic fields at launch? As instruments get faster and wider in their gaze, the sample will grow, and the statistics will sharpen. If the fiercest light rules the short flash category, GRBs are our champion, but the long game belongs to a different beast, one that keeps the lights blinding for millions of years instead of seconds. To meet that contender, we drift to the centers of young galaxies, where supermassive black holes feed and quasars turn gravity into a lighthouse visible across cosmic time. Shift your gaze from flashes to furnaces. A quasar is a lighthouse welded to the heart of a galaxy, powered by a supermassive black hole that eats gas and turns the fall into light. Where a gamma-ray burst is a matchhead that flares and goes out, a quasar is an arc lamp that refuses to dim. For millions of years it outradiates every star around it. On the scoreboard of sustained power, this is the heavyweight. Here is the engine, in plain terms. Gravity pulls gas inward. Before the gas crosses the point of no return, it piles into a whirling disk. Friction, particles rubbing, and magnetic fields tangling heats the flow to millions of degrees, so it shines from X-rays to infrared. The efficiency is astonishing. Roughly a tenth of the rest mass becomes radiation, and for fast-spinning black holes, it can climb to a few tenths, far beyond any chemical or nuclear engine we build. Numbers help anchor the scale. Our sun shines at about 4 × 10⁻26 watts. Bright quasars radiate up to 100 trillion suns, about 10 to the 40th watts, not as a spike but as a steady blaze. Some of that light comes from the inner disk, some from a hot coronal layer that boosts photons to X-rays, and, in radio-loud cases, some from jets, twin particle beams flung from the poles by magnetic fields wound tight as springs. There is a natural ceiling to a steady lamp. If radiation pushes outward too hard, it blows the inflow away. The balance point is the Eddington limit. Many quasars sit near that ceiling, bright as gravity allows without choking off their own fuel. That balance explains why their output can stay high for long stretches without exploding or fading at once. Not all quasars look the same from Earth. If a polar jet points at us, the core appears as a blazar, where beaming magnifies brightness and variability. Flux can double in hours, which means the emitting region is compact. Electrons in the jet spiral in magnetic fields and radiate, and the same electrons can upscatter softer photons into gamma rays. Quasars are not just bright, they are loud in their surroundings. Their light ionizes gas tens of thousands of light years away. Their winds blow at thousands of miles per second. Their jets pierce the galaxy and inflate lobes in intergalactic space. In galaxy clusters, those jets carve bubbles in the hot gas. X-ray images reveal cavities like footprints. The energy dumped there is vast enough to keep the gas from cooling and forming stars too quickly. In that sense, quasars are thermostats. They throttle how fast galaxies grow. This feedback writes itself into galaxy shapes. Many massive galaxies today have quiet centers and old stars. One path to that calm is a quasar phase in youth that heated or expelled the supply of cold gas, quenching star formation. If you could ride toward a quasar, what would you see? From afar, a star-like point outshining its host. Closer, the nucleus blooms into a brilliant core, with broad emission lines from fast gas clouds whipping around the center. The disk's inner rings orbit at a few % of light speed. Magnetic fields twist into corkscrews. Above the poles, funnels open where radiation and fields launch the jets. We know these pieces belong together because different telescopes catch different parts in the act. Radio arrays image the jets and lobes stretching for hundreds of thousands of light years. Optical and ultraviolet spectra show broad and narrow emission lines from gas at different speeds and distances. X-ray telescopes watch the corona flicker. When brightness lurches across bands in step, models that tie disk, corona, and jet gain credibility. By timing how broad lines echo changes in the continuum reverberation mapping, astronomers even weigh the black hole and sketch the inner architecture. A quasar's appetite needs a supply chain. Galaxy mergers can drive gas inward. Bars and tidal forces funnel fuel to the center. The same gravity that feeds the whole can trigger starbursts, so a galaxy can be both a stellar nursery and a quasar factory. Over time, the black hole bulks up. Observations show a loose link between a galaxy's central black hole mass and the mass of the host's bulge, a hint of two-way growth. The galaxy feeds the hole. Feedback from the hole shapes the galaxy. Do quasars switch off? Yes, they are episodic. Fuel runs low, or feedback overcooks the kitchen, and the core dims. The engine can nap for thousands of years and roar back when a fresh stream arrives. That stop-and-go behavior explains faint echoes, ionized clouds still glowing from a quasar that has already faded. If gamma-ray bursts hold the trophy for the brightest flash, quasars hold the belt for staying power. For millions, even hundreds of millions of years, they keep a city of galaxies worth of power running. They turn gravity's fall into light with unmatched efficiency. They reshape environments from parsec scales to cluster cores, and in special alignments where jets point at us, they rival short-lived dramas while still carrying the long, steady burn of the disk beneath. Power has more than one face. We have met the instantaneous spike of colliding black holes and the fiercest beam of light in gamma-ray bursts. With quasars, we crown the champion of endurance. Next, we tighten the lens from galaxy-wide lighthouses to city-sized engines. We will visit neutron stars so compact that a teaspoon of them outweighs a mountain. And in their most extreme form, the magnetar, we will find power concentrated into volumes smaller than a city, fierce enough to crack their own crusts. Shrink the scale from galaxies to something the size of a city. A neutron star is a sun's core crushed so tightly that a teaspoon would weigh more than a mountain. Pack more mass than the sun into a sphere about 20 kilometers wide, and you get gravity that funnels light into tight paths, matter compressed into neutrons, and a crust so rigid it can store titanic stress. This is power distilled, not spread across space, the clearest example of intensity per cubic meter that nature provides. How does such a tiny thing light up the universe? Start with rotation. Newborn neutron stars can spin dozens, even hundreds of times per second. That spin is a bank account of energy. Thread the star with a magnetic field and the rotation slows, bleeding power into beams from the poles. When those beams sweep past Earth, we see a pulsar, a lighthouse that ticks with clockwork precision. Now turn the dial from strong to extreme. A magnetar is a neutron star with a magnetic field so intense it warps atoms. Where ordinary pulsars carry fields 1 trillion times stronger than a fridge magnet, magnetars can reach 1,000 times beyond even that. In such fields, electrons are forced into single-file lines and atomic structure flattens. When it cracks, an actual starquake, magnetic lines snap and reconnect, and the star erupts in X-rays and gamma rays. Sometimes that snap is colossal. Astronomers have recorded giant flares that begin with a blinding spike and then ring down in pulses as the star vibrates. For a fraction of a second, the power near the source becomes almost unthinkable, and even from tens of thousands of light years away, the flash can saturate detectors and disturb Earth's upper atmosphere. It is not the most power in all the universe, but it may be the most power crammed into a city-sized engine. That is the point of power density. Two black holes colliding briefly outshine the cosmos, but their arena spans hundreds of kilometers. A gamma-ray burst fires a jet that stretches across light years. A magnetar's engine sits inside a ball no wider than a major metro area. Magnetars win their weight class, even if they lose to black hole mergers on the absolute peak power chart and to quasars on the marathon of sustained output. Magnetars do not only flare, they simmer. Many pop off with smaller, repeated bursts as the crust and fields settle. Their surfaces are hot by neutron star standards, and their steady X-ray glow fades over thousands of years as the fields unwind and the star cools. Some show sudden changes in spin, called glitches, brief speed-ups that hint at a handshake between the rigid crust and the superfluid interior. Peel back the surface, and the physics gets stranger. A thin atmosphere blankets a crystal-like crust. Beneath it, neutrons flow in a superfluid that slips without friction. Protons carry a superconducting current that locks to magnetic fields like rails. Twist the magnetar and these layers tug at each other, building stress until something gives. The shudder rings the star and shakes its magnetosphere. Radiation pours out as the geometry snaps toward a calmer state. Neutron stars show another face of power, gravity turned into light through accretion. In some systems, a neutron star orbits a normal companion and steals gas. The gas spirals in, heats up, and shines in X-rays. If the magnetic field is strong, it funnels the flow onto the poles, where impact points glow like hot spots that flicker at the spin rate. These X-ray pulsars convert falling matter to radiation with an efficiency far beyond any chemical engine and comparable to the best nuclear reactions. Spin can be rebuilt too. If a neutron star accretes long enough, it can be spun up into a millisecond pulsar, ticking hundreds of times per second with astonishing steadiness. These clocks are so stable that arrays of them across the galaxy act as a giant antenna for very slow gravitational waves, letting astronomers sense how spacetime swells and shrinks as titanic black holes orbit far away. Even here, power hides in timing. A tiny star, perfectly arranged, becomes an ear for the deepest bass notes in the universe. There is a human hook, gold rings, platinum contacts, and other heavy elements likely owe their existence to neutron star mergers and the kilonovae they trigger. When two neutron stars collide, their debris makes a radioactive fireball that fades from blue to red as it builds the periodic table's heaviest entries. Fast radio bursts add one more twist. These millisecond flashes of radio light arrive from across the sky with no warning. Some repeat, some do not. Magnetars make a compelling suspect. A sudden rearrangement of the magnetosphere could launch a shock into surrounding plasma and squeeze it to emit a coherent radio shout. So, where do neutron stars and magnetars sit in our tournament? For sustained power in a tiny package, neutron stars are unmatched. For power density, the most energy crammed into the smallest volume, a flaring magnetar is hard to beat. They cannot rival black hole mergers for instantaneous peak across the whole universe, nor can they match a quasar's million-year furnace. But, in the category of concentrated fury, they win. They are nature's proof that the universe can be both small and overwhelming. Keep this scale handy. Next, we pull back out to judge a quiet giant, the energy stored not in objects but in the emptiness between them. Before we crown any one champion, we have to weigh the slow, relentless push that accelerates the whole universe. That push is not a jet or a flare. It is a pressure with no nozzle, a force with no engine room, and yet it reshapes everything over billions of years. Call it power without a beam. Dark energy is not a jet, not a flare, not even an object. It is a pressure baked into empty space that makes the universe's expansion speed up. We discovered it by timing cosmic mile markers. Type Ia supernovae, which explode with near-standard brightness, were dimmer than they should have been for their redshift. That meant they were farther away than a slowing universe would allow. The only way to square the numbers was to accept that space is not just expanding, it is accelerating. Something is pushing, and that push is smooth, everywhere, and relentless. In everyday physics, pressure pushes outward. In cosmology, pressure also gravitates. The strange thing about dark energy is that its pressure is negative. In Einstein's equations, acceleration happens if the energy density plus 3 times the pressure divided by c squared adds up to a negative number. Vacuum energy, with pressure equal to minus its energy density, 1 equals 1-inch cosmologist shorthand, hits that condition exactly. Gravity then acts like a repulsive effect on large scales, not by turning gravity upside down, but by making the overall mass energy plus pressure term negative, so the scale factor picks up speed. What does it mean to call this powerful? A fair definition in our tournament is ability to do work on the universe, to change its motion. On that field, dark energy is the quiet champion. Once the matter in the universe thinned out enough, roughly 5 or 6 billion years ago, the vacuum term took over the expansion story. Since then, Galaxies not bound to us have been slipping away faster and faster. The farther they are, the faster they recede. Over deep time, the local group of galaxies will remain, but nearly everything else will fade beyond reach. That fate is written by a pressure you cannot point to, switch off, or shield against. Numbers help anchor the idea. The energy density tied to dark energy is tiny per cubic meter, on the order of a few times 10 to the minus 10 joules, roughly the mass energy of a handful of protons in a living room volume. Yet space is enormous, and the amount of space is growing. If you insist on a power figure, you can ask how fast the vacuum energy inside a Hubble-sized bubble increases as that bubble swells. The answer lands around 10 to the 52nd watts. That dwarfs any engine or event we have met. It is not power you can bottle, and global energy accounting in an expanding universe is subtle, but as a measure of influence, it is sobering. Dark energy behaves oddly compared to familiar stuff. If its equation of state number W is exactly 1, its density stays constant as space grows. Double the volume, and you get double the vacuum energy, which keeps the push steady. If W is slightly above 1, the density falls a bit with time. If it is below 1 phantom energy, the density rises and the expansion can run away toward a hypothetical big rip. Right now, the best observations say W is very close to 1 phantom, making dark energy look like a true cosmological constant. That means the universe's large-scale future trends toward a calm but accelerated de Sitter-like state, with a cosmic event horizon, a limit beyond which events can never send signals to us, no matter how long we wait. Because dark energy is uniform, it does not clump into structures. It will never make a star or a jet. Its influence shows up in smooth statistics, how the expansion rate changes with time, how the growth of galaxy clusters slows compared to a matter-only universe, how the pattern of galaxies on the sky stretches with redshift, and how light from the early universe carries imprints in the cosmic microwave background. Different instruments attack each clue in a complementary way. Supernova surveys measure distances. Baryon-acoustic oscillations trace a standard ruler in the galaxy web. Weak lensing maps how gravity bends light across vast fields. Together they sketch a cosmos that is roughly 1/3 matter and 2/3 dark energy, with the latter pulling the long-term strings. The strangest part is the scale mismatch between quantum expectations and what we measure. Simple quantum field arguments suggest vacuum energy should be mind-bogglingly larger than observed by many orders of magnitude. Yet the sky insists on a tiny value that only reveals itself across billions of light years. Why it is so small, why it is not exactly zero, and whether it is truly constant are open questions at the edge of physics. Maybe it is a property of space-time itself. Maybe it emerges from fields we have not seen. Maybe it varies in a broader multiverse and we live where galaxies could form. For now, it is a parameter we read from the sky, like a note on a score we cannot yet play ourselves. It is easy to dislike an answer you cannot hold in your hand, but the consequences are plain. Acceleration makes the cosmic web more brittle over time. Filaments thin, voids widen, and galaxy halos keep their own counsel. It alters the timing of when structures form and how long they keep accreting. It cools off the universe's social life. In a few tens of billions of years, observers in our remnant island of galaxies will see almost nothing beyond their neighborhood and might infer a different cosmic history if they did not find fossil clues in background light. As an entry in our power league, dark energy wins on scale and patience. It does not outshine a quasar per second in any single spot, and it does not spike like a black hole merger. Instead, it presses on everything everywhere, all at once, for eons. If we define power as the capacity to steer the universe's overall motion, dark energy is the reigning monarch. If we define power as energy density in a tiny box, magnetars take the belt. If we define power as raw instantaneous output, colliding black holes hold the crown. One word, many champions, We will keep dark energy's quiet rule in mind as we turn to the partner that builds the stage rather than pushes it apart. Dark matter does not shine, but it clumps, pulls, and sculpts. It is the keystone that channels gas into galaxies and feeds the engines we have already met. To judge the universe's most powerful processes honestly, we need to see the scaffold they ride on, and the largest mechanical brawls it hosts: galaxy clusters colliding at thousands of kilometers per second, where shock waves roll through clouds bigger than galaxies, and the energy budget rivals anything short of the vacuum itself. Shift your focus from the push of empty space to the scaffold that gives the universe its shape. Dark matter does not glow, yet it gathers, and gravity flows along what it builds. Imagine a vast, three-dimensional web made of mass you cannot see. Gas drifts into the web's filaments, cools in the densest knots, and lights up as galaxies. Without that invisible frame, stars would be scattered sparks. With it, matter funnels into cities of light. You feel dark matter's power through motion. Galaxies orbit centers heavier than their visible stars. Groups fall into clusters that hold hundreds of galaxies swimming in a hot sea of gas. That gas reaches tens of millions of degrees and shines in X-rays, yet even gas plus starlight cannot account for the gravity you infer from the speeds involved. Something unseen does most of the pulling. In clusters, that something outweighs what we can see by roughly 5 to 1. If power means the ability to move mass over time, dark matter ranks high. Its clumps set the stage on which galaxies form, collide, and grow. Over billions of years, dark matter halos merge the way rivers join, building larger structures step by step. The most dramatic steps are cluster collisions, where metropolises of galaxies plow through each other at thousands of kilometers per second. Their different kinds of matter separate and reveal their natures. Here is the choreography. The galaxies are small and sparse compared to a cluster, so most pass by without direct hits. Dark matter interacts almost only through gravity, so its halos also slide through. But the gas between galaxies is thick on cluster scales. When two clusters collide, their gas clouds ram, shock, and slow. A bow wave forms, heating the gas and leaving it behind the collisionless galaxies and dark matter. If you map the hot gas in X-rays and then map total mass by gravitational lensing of background galaxies, you get two different pictures: gas lags, mass leads. The bullet cluster made this separation vivid. A smaller cluster punched through a larger one, like a supersonic round. The gas was knocked aside and lit up in X-rays, while the bulk of the mass, traced by how it bent the shapes of far-behind galaxies, kept going with the galaxies themselves. Similar offsets show up in other mergers such as El Gordo and Max, JWST. These crashes are brutal, but they double as experiments. If dark matter bumped and stuck like gas, the mass peaks would lag behind. They do not, which tells us dark matter interacts very weakly with itself. Why include this in a story about the most powerful things? Because cluster mergers move energies that rival anything short of the vacuum's global push. Think of the kinetic energy of hundreds of trillions of suns crashing together across millions of light years. Shock fronts roll through the gas and light up radio relics, long arcs, where electrons have been whipped to near light speed and spiral in magnetic fields. Behind the shocks, turbulence stirs the intracluster medium for hundreds of millions of years, mixing and heating as it goes. Put numbers to the picture to feel the scale. A rich cluster can weigh a quadrillion suns. Two of them colliding at 2,000 kilometers per second carry kinetic energies around 10 to the 64 joules. The shocks they drive can span a few megaparsecs with Mach numbers of 2 or 3. The heated gas glows for gigayears. Measured as power, the energy transfer per second is modest compared to a quasar's glare. Measured as work on matter, it is colossal, stirring and heating volumes larger than galaxies. Power also hides in how dark matter bends light. Gravitational lensing squeezes, stretches, and multiplies the images of faraway galaxies. In strong cases, arcs and rings appear. In weak cases, the average shapes of many background sources tilt in a preferred direction. Both effects let astronomers weigh halos without touching them. The heavier the halo, the stronger the lens. In clusters, lensing maps reveal clumps within clumps, like districts inside a city, showing sub-halos that survive long after major mergers. The web that halos weave stretches between clusters as filaments. These bridges are faint, but their gravity guides galaxy motions and channels gas. Where several filaments meet, clusters grow fastest. Like cities at the crossing of highways, observations map filaments by lensing and by faint X-ray and microwave fingerprints of warm gas. Simulations turn those clues into time-lapse movies of structure rising from tiny ripples in the early universe to the foam-like cosmic web we see today. This matters because energy flows along the channels dark matter lays out. Gas cooling into a filament feeds a galaxy that can light up as a quasar. A merger that perturbs a halo can send fresh fuel to a central black hole or spark a wave of star formation. Even the fiercest engines ride the rails of the dark web. Remove the rails and the traffic thins to almost nothing. In our tournament, where does dark matter stand? It wins no trophies for brightness. It does not match the spike of black hole mergers or the tight fury of magnetars. Yet as a mover of things, as the organizer of flow, it is second only to dark energy in reach. It creates the stage on which quasars burn, on which gamma-ray bursts crackle, on which clusters collide. If power is the ability to steer the fates of visible matter over time, dark matter is one of the universe's senior engineers. Keep that engineer in mind as we turn from the web to the engine room of gravity itself. We have visited shocks in cluster gas and the quiet pull of halos. Next, we dive into the anatomy of a black hole, not as a metaphor but as a machine that converts in falling mass into light, jets, and, in the end, the ripples that make the universe ring. Open a black hole as if it were a machine and label the parts in plain language. At the center sits a region where our current physics fails a singularity. Around it is a one-way surface, the event horizon. Cross it, and no signal returns. Outside that boundary, the engineering we can study takes place. Infalling gas builds a bright, whirling accretion disk threaded by magnetic fields. If the hole spins, its rotation drags spacetime. The disk forms because infalling gas has sideways motion. Instead of plunging straight down, it circles, rubbing against itself and heating up. Close to the hole, the orbit that can stay stable ends the inner edge called the ISCO, the innermost stable circular orbit. The location of that edge depends on spin. For a non-spinning hole, the ISCO sits at 3 times the Schwarzschild radius. For a rapidly spinning hole, prograde orbits skim much closer. The closer the edge, the deeper the gravitational well the gas falls through and the greater the efficiency. A thin, radiatively efficient disk can turn about 10% of rest mass into light. With fast spin, the figure can be several tenths, far beyond nuclear fusion. What does the disk look like? That depends on mass. Around a stellar mass black hole, inner disk temperatures reach millions of degrees and radiate mainly in X-rays. Around a supermassive black hole, the inner disk is cooler per unit area and shines mostly in ultraviolet and optical light, while a hot coronal veil upscatters some photons into X-rays. That corona leaves fingerprints, broad iron lines, and a reflection spectrum bent by strong gravity, letting astronomers map the inner few gravitational radii. Spin adds a second dial. A rotating black hole drags spacetime around with it. This frame dragging is strongest in the ergosphere, a region just outside the horizon where nothing can remain still relative to distant stars. Tap that rotation, and you can extract energy. In real galaxies, the clean route is electromagnetic. Magnetic fields anchored in the disk and threading the horizon act like wires on a spinning flywheel. The result, called the Blandford's-Najek process, launches pointing flux jets that carry away rotational energy. Jets demand more than spin. They need magnetic flux, lots of it piled up near the hole. If the inflow drags enough field inward, it can choke itself into a magnetically arrested disk. In that mad state, jet power can rival the disk's radiative output. The narrow beams accelerate particles to near light speed and inflate lobes far beyond the host galaxy. Point a jet almost at us, and we see a blazar, brightened by relativistic beaming. Even without grand jets, the inner flow is a workshop of variability. Turbulence driven by the magnetorotational instability behaves like friction, transporting angular momentum outward so mass can spiral inward. At low feeding rates, the flow can puff up and radiate inefficiently. At high rates, it thins into a bright lamp that pushes toward the Eddington limit, where outward light pressure counters gravity. Evidence that this machine picture is real comes from many fronts. X-ray binaries, stellar mass black holes feeding from companions, cycle between states that match expectations for disks, coronas, and jets. Supermassive black holes show the same grammar scaled up by mass. Reverberation mapping times the echo of coronal flickers off the disk to measure sizes in light minutes. The Event Horizon Telescope imaged the shadows of nearby giants, revealing rings whose sizes match strong gravity predictions. The same engine also sets the stage for the universe's strongest spikes. Two black holes that spiral together arrive already spinning and, in gas-rich neighborhoods, wrapped in disks. As they merge, gravitational waves carry away energy and angular momentum. If leftover gas remains, shocks and magnetic twist can light a brief electromagnetic afterparty, though most of the energy still leaves as ripples in spacetime. In mergers of neutron stars, a black hole plus a hot, magnetized disk can fire a short gamma-ray burst, gravity's fall turned into a beam of light by the same jet physics. From a human perspective, the scale is both tiny and vast. The horizon of a 10 solar mass hole spans only tens of kilometers, smaller than a city, yet when well fed, it can outshine billions of suns. The horizon of the 4 million solar mass hole in the Milky Way spans microarc seconds on the sky, and its neighborhood still fits inside the solar system. The same equations describe both engines, only the clock speed changes. Power also hides in winds. Not all inflowing gas makes it through the last gate. Radiation pressure and magnetic stresses can fling a large fraction back out as wide-angle outflows. These winds carry mass, momentum, and energy into the host galaxy, where they can heat gas, quench star formation, or compress clouds and trigger it. Repeated jet episodes carve cavities in cluster gas. The work done inflating those bubbles balances cooling and prevents runaway star formation. If you could listen to a black hole engine, you would hear quasi-periodic oscillations hums with notes that may track orbital frequencies near the ISCO. You would hear flicker from turbulence, punctuated by jet shots when magnetic tension snaps. The soundtrack changes as fueling rises and falls, but the score is written by gravity and magnetism playing off rotation. So what crown does the black hole engine win in our tournament? It is the most efficient mass-to-light converter known, the most versatile power plant across scales, and the hub that ties together several of our champions. Feed it slowly and it hums, feed it fast and it roars, thread it with field and it throws jets that sculpt galaxies, smash two together and it rings the universe like a bell. If you want a single mechanism that turns gravity into observable power, a spinning black hole plus a magnetized disk is your answer. Next, we step from engines to calibration. We will translate the dizzying numbers into familiar terms, watts, joules, years, and stack them against rockets, lightning, and every power plant on Earth. So the rankings become quantities you can hold in your head. Translate the sky's numbers into ones your gut can feel. Start with units. A watt is 1 joule per second. A joule is the energy to lift a small apple about a meter. Your phone charger hums at tens of watts. A microwave cooks at about 1,000. A big power plant makes 1 billion. All of humanity, averaged over the year, runs near 20 trillion watts. That is our baseline hum. 20 trillion apple lifts every second. Now climb from our hum to nature's engines. A lightning bolt spends roughly 1 billion joules in a few thousandths of a second, so its power, while it flashes, is about 1 trillion watts. A Saturn V at liftoff poured out roughly 40 billion watts of chemical power, dozens of big plants strapped together for a couple of minutes. A major hurricane's heat engine runs near 100 trillion watts as vapor condenses into rain. Sunlight falling on Earth's day side totals about 170 quadrillion watts. The sun itself shines at roughly 3.8 times 10 circumflex 26 watts. Here is a ladder from ground to sky. Humanity to 2 times 10 13 watts. Hurricane to 10 circumflex 14 10 15 watts. Lightning to 10 12 watts, but only for instance. Saturn V to 4 times 10 10 watts. Sunlight on Earth to 1.7 times 10 17 watts. The sun to 4 times 10 26 watts. Each step is enormous. The cosmic steps dwarf them. Now place our champions. A bright gamma-ray burst reaches an isotropic equivalent luminosity near 1045 watts. Because the jet is beamed into a cone only a few degrees wide, the apparent brightness along the beam can look even fiercer. Compared to the sun, 1045 watts is about 10 million trillion times brighter in that moment. Compared to the global human grid, it is 30+ orders of magnitude higher. Quasars play the long game. A top-tier quasar radiates around 10.40 watts steadily for millions of years. That is 27 orders above the human power budget, 14 above a hurricane, not for minutes or days, but long enough to remodel a galaxy. Integrated over 10 million years, that is roughly 3 times 10 circumflex 54 joules. A typical supernova releases about 1044 joules of light. 100 million of them still trail a quasar's burn. Magnetars win on concentration. A giant flare can release as much energy in a fraction of a second as the sun emits in minutes, packed inside a sphere about 20 kilometers across. The absolute peak is below the brightest gamma-ray bursts, but the power per cubic meter is astonishing. The spike crown belongs to colliding black holes. In the last split second before merger, their gravitational wave power peaks near 1049 watts. The sun's luminosity multiplied by roughly 100 billion, likely exceeding the combined starlight of the observable universe during that instant. Imagine all power plants on Earth, every storm, every rocket engine firing at once, then multiply by numbers that make zeros spill off the page. That is a single chirp. Dark energy plays a different numbers game. Per cubic meter, its energy is tiny, but space is vast and growing. Ask how quickly the vacuum energy inside a Hubble-sized bubble increases as the bubble expands, and you get a notional power around 1052 watts. You cannot tap this, and bookkeeping in an expanding universe is subtle, but as a measure of influence on motion, it is the heavyweight of patience. Flip the question. How much energy sits in familiar stuff if you turned all its mass into light? MC2 says a kilogram embodies about 90 quadrillion joules. A liter of water equals a large hydrogen bomb. The sun contains roughly 2 times 1027 joules of rest mass energy. Over its life, it radiates only a small fraction, because fusion is stingy, converting under 1% of the sun's mass to light. A thin, fast accretion disk around a spinning black hole can convert several tenths an efficiency unmatched by any other steady engine. Some trades make the scale visceral. The electricity the world uses in a year is roughly 6 times 1020 joules. A single bright second of a gamma-ray burst can beat that by 1 trillion. The largest thermonuclear test released about 2 times 1017 joules. A top quasar tosses that much energy in less than a microsecond and keeps doing it for millions of years. A giant magnetar flare dumped enough energy to disturb Earth's upper atmosphere from tens of thousands of light years away. Channel matters as much as raw numbers. Light heats and pushes. Jets carry momentum and inflate radio lobes bigger than galaxies. Gravitational waves carry pure curvature and cross the cosmos unscathed. Dark energy changes the expansion itself and quietly decides which regions can ever exchange signals. With the ladder in view, we can rank with honest caveats. Instantaneous peak power, black hole mergers. Brightest beam of light, gamma ray bursts. Highest power density, magnetars and neutron star smash-ups. Most sustained luminosity, quasars and their jetting cousins. Largest, slowest influence on motion, dark energy. Most decisive organizer of where power flows, dark matter. None cancels the others. They are champions of different weight classes. Keep these conversions handy as we turn to extreme case studies. Next, we will dissect one famed gravitational wave event, one record-setting gamma-ray burst, and one blistering quasar, translating each into watts and joules and everyday analogies so the numbers land not just on paper, but in your bones. Let's retell 3 real cosmic moments in plain, everyday language, with pictures in your mind instead of formulas on a page. Think of this as a tour through 3 scenes. A ripple you cannot see but can measure, a beam of light that acts like a cosmic spotlight, and a long burning furnace that refuses to dim. First story. The day the universe chirped. In September 2015, 2 distant black holes finished a long dance and became one. We did not see a blinding flash. We felt a tiny shiver in the fabric of space itself. Imagine a calm lake. Far away, someone drops a pebble. A delicate ring spreads out, and much later, the ripple brushes past your toes. That is what reached Earth. A ripple in space-time so faint that our detectors had to notice a stretch smaller than the width of a proton, along arms 4 kilometers long. That quick rise and fall told us, in one breath, that black holes are real, that they collide, and that space can carry news of their union across 1 billion light-years. Second story. The brightest beam of light nature has ever pointed our way. In October 2022, satellites saw a sudden spike of high-energy light that broke records. Astronomers nicknamed it the boat, the brightest of all time. Picture a heavy star at the end of its life. Its core gives way, a newborn black hole forms, and 2 needle-thin jets erupt from the poles like twin blowtorches. Most of the time, those beams point elsewhere. This time, one lined up almost perfectly with Earth. That alignment made it look unbelievably bright, the way a stage spotlight looks blinding if it points at your eyes. For minutes, the burst outshone everything around it in high-energy light. After the first spike, the fading afterglow let telescopes trace the blast as it plowed into surrounding gas. From the way the glow changed with time and color, astronomers read out the story of the jet. How narrow it was, how fast it moved, and how dense the neighborhood was. Even dust in our own galaxy got involved, scattering the light into faint rings that expanded across the sky like ripples in a pond. The headline was simple: when one of those jets points our way, nature's flashlight is fierce. Third story. A furnace that refuses to quit a nearby, well-studied quasar. At a quasar's heart sits a supermassive black hole, millions to billions of times heavier than the Sun. Gas spirals inward around it, forming a hot, bright disk. Gravity turns that fall into light with astonishing efficiency, far better than any engine humans have built. The result is not a flash, but a long, steady blaze. Imagine a city where every window is lit, every street lamp is on, and it stays that way not for hours or days, but for millions of years. Some quasars also launch twin jets that drill out of the galaxy and inflate huge lobes in intergalactic space. Those jets push on their surroundings, carving bubbles, heating gas, and, over time, slowing the birth of new stars. In that way, a quasar is both a lighthouse and a thermostat. It lights the universe, and it sets the temperature of its neighborhood. Put the 3 together, and you get a clean scoreboard without needing a calculator. The black hole chirp wins for the tallest spike, the biggest burst of power in the shortest time. The gamma-ray burst wins for the fiercest beam, the most intense light along a very narrow path. The quasar wins for endurance, the longest, steadiest burn, bright enough to remodel its entire region. Different champions, different weight classes, one vast arena. Why care beyond the wow? Because these events are not just fireworks, they are tools. Black hole chirps let us test gravity where it is strongest and measure distances across the universe in a brand new way. Bright bursts teach us how massive stars die and where some of the heaviest elements are forged, gold and platinum among them. Quasars show how young galaxies grow up, when they burn fast and when they settle down. Taken together, they sketch a life cycle. Gravity gathers gas, engines ignite, energy flows out, and the cycle resets as new stars and planets appear. There is also a quiet lesson. The universe can be incredibly loud and incredibly gentle at the same time. The power in a black hole merger can beat the light of all the stars, yet the wave that reached Earth was softer than a whisper and took decades of careful engineering to notice. The brightest burst we have ever seen still arrived as a thin rain that our satellites had to catch against the steady glow of space. A quasar's roar spans every color of light, yet, to our eyes, it is just a sharp point in a telescope. Huge effects, delicate signals. That is the rhythm of modern astronomy. If you want a one-sentence summary to keep in your pocket, here it is. The most powerful instant we have caught is a black hole merger. The most powerful beam we have caught is a gamma-ray burst aimed at us. The most powerful long-term engine we have caught is a quasar. None replaces the others. They rule different categories, and each one is a real, recorded piece of the cosmos, not just an idea on a chalkboard. Now that the rankings make sense in everyday words, we can safely peek beyond the familiar. There are ideas on the cutting edge that might produce even stranger shows, relics from the universe's first moments, hypothetical strings in space that could snap like over-tight guitar wires, or rare space-time tricks we have not yet seen. Most will stay maybe until better data arrive. In the next section, we will visit a few of them carefully, keep the language clear, and judge them by a simple test. What would each one actually look like in the sky? And how would we know it for real? Step to the edge of certainty and look over the railing. We have crowned champions we can measure: black hole chirps, record bright bursts, and long-burning quasars. Now, let's visit the rumor mill of the cosmos. Bold ideas that might outmuscle our winners if they are real, and how we would recognize them without drowning in math. Cosmic strings. Imagine hair-thin seams left from the universe's first instant, stretched across space like guitar wires under crushing tension. They are not ropes of matter, they are wrinkles in space-time itself. If two strings crossed and sliced, or if a loop shrank and vanished, the release could send a fast, clean ping of gravitational waves. To us, it would look like a sharp, short wiggle in our detectors, more of a click than the rising chirp of merging black holes. White holes. A black hole is a one-way door in. A white hole, on paper, would be a one-way door out, like a hydrant that only sprays. Most physicists think tidy, long-lived white holes are unstable. Anything nearby would fall in and spoil the rule. But some ideas say a tiny black hole could bounce after an unimaginable time and dump its stored energy in a flash. It might appear as a brief, odd-colored burst that does not quite match any known fireworks. Black hole spin drain. Superradiance. Spin up a black hole and thread it with the right kind of field, and it can slowly give up its rotation, like a whirring top that hums down. In some versions, the energy builds a faint cloud around the hole and leaks away as a nearly steady tone of gravitational waves. Not a flash, but a long, pure note in the background, one violin heard through the noise of a crowd. That would be a new kind of power plant, a dark flywheel feeding the universe with a quiet song. Vacuum decay. Our empty space might not be the deepest kind of empty. It could be a false floor. If a lower floor exists, a tiny bubble could appear somewhere, then race outward at almost light speed, changing the rules inside it. Atoms, chemistry, Even light could behave differently there. There would be no warning and no shield. What would we see? Nothing, because we would be rewritten before we could watch it happen. Current clues say not to worry, but the idea reminds us that power can hide in the calm. The Big Rip. If the push that speeds up the universe grows stronger with time, it would do more than separate galaxies. Step by step, it could pull apart clusters, galaxies, solar systems, and in the far future, even atoms. Today's measurements favor a steady push, not a rising one, so a rip looks unlikely. Still, it is a reminder that the quietest force on our list could, in some futures, be the loudest ending. Hidden engines inside stars. If new, barely there particles exist, they could carry energy out of stellar cores and change the timing of star death. That would tweak how often certain supernovae happen and how heavy elements are made. We would not notice a single wow event. We would notice a pattern the way a long season of small gusts moves more sand than one storm. This would be quiet power, written across millions of stars. New messengers arriving together. We already have light, gravitational waves, and ghostly particles called neutrinos. The day we catch all three from one source, say, a collapsing star with a jet, the engine's power budget will snap into focus. We will know how much energy left as light, how much left as ripples in spacetime, and how much left as particles that ignore almost everything. That triple hit will not create a new champion, but it will let us score the game fairly. How do we keep our feet on the ground while we peek at the wild edge? We use two simple tests. First, make a movie in your head. What would the sky actually do? Flash, hum, or ring? A good idea can describe its own trailer in plain words. Second, name the weight class it claims to win. Tallest spike, brightest beam, longest burn, most concentrated, widest reach. Most powerful only means something if we say at what. Here is the honest part. The universe has already humbled us. We did not expect a black hole merger to pour out more power than starlight, yet touch our instruments more softly than a whisper. We did not expect a single beam of light to reset our records in an afternoon. We did not expect a quiet furnace in a galaxy's heart to throttle star birth across a cluster. So we listen wide and keep our yardsticks simple. When a bold claim arrives, we will ask, what did the sky do, and how much did it move? If even one of these edge ideas turns out to be real, our leaderboard will shift. A snapping cosmic string could post a new kind of spike. A spin-drained black hole could add a permanent note to the universe's background music. A white hole-like bounce could explain a puzzling one-off flash. And if the triple arrival of light, waves, and neutrinos becomes routine, our box scores will change from guesses to audits. But the deeper thread does not change. Every rumor on this list is really about how the universe moves energy around, storing it in tension, in spin, in empty space, releasing it in a snap, a hum, or a slow push. The details may shift. The grammar stays. Gravity gathers. Fields store. Engines ignite. Energy flows. Matter remembers. Next, we come back from the frontier to your backyard. On a clear night, with your eyes, what are the most powerful things you can actually see, and how do they connect to the titans we have met? The bridge from a quiet patch of sky to the biggest power plays in the universe is shorter than it looks, and walking it makes the numbers feel human. Step outside on a clear evening and let your eyes adjust. You're not looking at a flat ceiling, you're peering into a living power grid. The calm glow above you is energy on the move, and a lot of it is visible with no tools at all. We've crowned champions that need satellites and super detectors. Now, let's keep it simple. What can you actually see, and how do those sights connect to the biggest engines in the universe? Start with the nearest powerhouse you know by heart, the sun. You can't stare at it, but every shadow and warm breeze around you is its work. Deep inside, the sun runs a steady fire that sends light across space and paints our sky blue. Compared to a black hole engine, the sun is gentle and dependable, and that steadiness is exactly why life can use it. During a total eclipse, when the moon briefly hides the glare, the sun's outer atmosphere appears as a pale crown. Those soft streamers are shaped by invisible magnetic fields, a quiet reminder that the same forces that launch cosmic jets also sculpt our own star. After sunset, the sun's touch wears a different costume, the aurora. If you live far north or south, you may have watched curtains of green and purple slide across the sky. That is the solar wind, a river of tiny charged particles pouring into Earth's magnetic shield. The field guides that river toward the poles, where it shakes atoms high above us and makes them glow. A quiet planet turns into a slow-motion light show. Big storms on the sun can turn the brightness up, a reminder that our weather stretches from ground to space. Now meet the bright wanderers, Venus, Jupiter, and Saturn. Venus blazes because it's close and wrapped in reflective cloud, a tiny mirror for the sun. Jupiter, even from a city, is a small white ember. With simple binoculars, its 4 big moons pop into view, lined up like a pocket solar system. Those moons taught Galileo that not everything circles Earth, and they still teach us about hidden power. The closest, Io, is covered in volcanoes, because Jupiter's pull kneads it like dough and heats it from within. That is gravity turning motion into warmth, the same trade that powers the biggest crashes between galaxies, only here it plays out on a world you can actually glimpse. Lift your eyes to the Milky Way, a pale speckled river arcing from horizon to horizon. In town it hides, outside the city it returns. You're seeing our home galaxy from the inside, starlight and dark dust stacked along your line of sight. Near the middle, behind thick curtains of dust, sits a black hole a few million suns in mass. It's quiet now, a campfire more than a lighthouse, but it's built on the same plan as the monsters that light up as quasars. Long ago it likely flared brighter, stirring gas and shaping the neighborhood on a gentler scale. But with the same grammar, gravity gathers, fields guide, energy flows. Trace a winter pattern, Orion. In his sword hangs a fuzzy patch you can spot with your eyes if the night is dark. That patch is the Orion Nebula, a real star nursery. Cold gas gathers, newborn stars switch on and flood the room with light, carving caverns and pillars. This is the opening chapter of the energy story. Clouds collapsing, stars igniting, and soft jets blowing bubbles that future stars and planets will grow inside. Not far away on the sky lies the Crab Nebula, the wreckage of a star that exploded long ago. In its heart sits a tiny, rapidly spinning star that beats out energy like a metronome. One view shows birth, the other shows aftermath. Both are power moving from place to place. Sometimes the sky brings power to you. A meteor streaks overhead and, for a second, the air hisses with light. The glow isn't the rock burning like a match. It's the air itself heated until it shines as the rock plows through at extreme speed. A bright fireball can leave a smoke ribbon that twists in high winds long after the flash is gone. It's a small, honest lesson in how motion turns into heat and light. In an instant, the same rule that bigger engines use, just scaled to something you can watch from your porch. Raise your eyes to Andromeda on an autumn night. If the sky is truly dark, you can spot it as a faint oval. You're looking at another galaxy with 1 trillion stars, naked eye proof that the universe doesn't end at our doorstep. In a few billion years, Andromeda and the Milky Way will drift together and merge. Stars will mostly pass by without hitting, but clouds of gas will collide, shock, and warm up. The night sky will reshape itself slowly, like a city changing over centuries. It won't be a destructive smash, it will be a long dance. On that huge stage, the power isn't a single flash. It's work spread across time, exactly the kind of slow, steady influence we gave to dark matter and dark energy in our rankings. You can even watch timing at work from your window. Betelgeuse, the orange star in Orion, swells and shrinks over months as its outer layers breathe. One day it will end in a supernova. That day may be far off, but the idea connects directly to the gold in a ring and the calcium in your bones. Stars are foundries. When they die, they seed space with heavy elements. and new stars and planets form from that enriched dust. The power that lights the sky also builds the matter we touch. If you have no dark sky, you still have a sky. The International Space Station crosses like a bright, steady dot at dusk. That is sunlight on metal, a moving mirror that says the sun powers our machines, just as it feeds our weather and our food. Even city clouds carry the story. Their shapes ride on heat rising from buildings and streets, driven by sunlight stored during the day and released at night. The same rules that glow in a nebula hum in a streetlight, only gentler. All these sights tie back to our earlier champions with one simple path. Gravity gathers, fields shape, engines ignite, energy flows. The sun is the gentle engine we live by. Auroras are its breath curling along magnetic lines. Jupiter's moons show gravity's tug turned into warmth. The Milky Way's band hides a quiet black hole that once may have flared like a small lighthouse. Orion's cradle and the crab's wreck show birth and death sharing the same sky. Andromeda shows the slow choreography that builds and rebuilds galaxies. The backyard view and the deep space view are not separate stories. They're the same story at different scales. When you walk back inside after a good look up, keep one picture in your pocket. Every soft glow and quick streak you saw is part of the same river of power that, at its extremes, becomes a black hole chirp, a record-bright burst, or a quasar's roar. The difference is scale and timing, not the rules. The universe writes with the same ink on every page, sometimes in big, loud strokes, sometimes in fine print you can read with your own eyes from your backyard. How do we know any of this is true without equations? We read the sky like a detective reads a room by traces anyone can picture. Light is the first witness. Color carries heat. Bluer is hotter. Redder is cooler. Split light with a prism and you see a barcode of lines. That barcode tells us which elements are present and whether the source is moving away or toward us. A red nudged barcode means it's receding. Blue means approaching. From that simple shift we clock galaxies and jets and learn that space itself is expanding. Brightness is the next witness. If you know how bright a kind of object truly is, you can tell its distance by how faint it looks, like judging how far a car is by its headlights. Some supernovae behave so consistently that they act as standard headlights. Comparing true brightness to apparent brightness showed that faraway galaxies are farther than a slowing universe allows, pointing to a gentle push built into space, dark energy. Timing is a third witness. The faster something flickers, the smaller it must be. A quasar that changes in a day can't be bigger than a light day across. A sudden bend in a gamma ray burst's fading glow tells us our view has reached the edge of a narrow beam. A tiny dense star that glitches for a moment reveals the handshake between its hard crust and liquid-like interior. Fast change means a compact engine, no formulas required. Shadows add another clue. Linking radio dishes across Earth made a planet-sized eye that drew bright rings with dark centers around nearby giant black holes. The dark patch isn't the hole. It's where light paths curve so sharply that little reaches us. Its size and shape match what gravity predicts at a black hole's edge. Our closest look at the boundary, where in becomes gone. Lenses let us weigh what we can't touch. Mass bends light, so a heavy galaxy cluster acts like a magnifying glass for anything behind it. Background galaxies look stretched or wrapped into arcs. From that warping, we measure total mass, visible and invisible, the way a trampoline's sag hints at weight. In cluster collisions, glowing gas lags, while most of the mass, traced by lensing, sails ahead. That split shows the bulk is invisible and almost non-sticky. Dark matter. Ripples are the newest messenger. Gravitational waves don't glow. They stretch space. A chirp is a rising tone as two heavy bodies spiral together. We don't listen with ears, we listen with rulers. Lasers run down long tunnels and bounce off mirrors. When a ripple squeezes one tunnel and stretches the other, the returning light flickers. It's the faintest tide imaginable, yet it carries news from billions of light years away. Sometimes, messengers arrive together. In one famous crash of two tiny dense stars, a ripple in space came first. A short flash of high-energy light followed, and hours later, a new point of light blossomed and faded from blue to red as heavy elements formed. One event, three channels, one story. Motion turned into light and matter for future worlds. There are quieter tests. If a beam points at us and then dims too fast, it's probably widening like a flashlight whose beam blooms even though the batteries are fine. If a quasar's glow flickers across colors at slightly different times, we can map which parts of its inner disk light up nearby gas. Giant bubbles in a cluster's hot gas reveal repeated pushes from buried jets. These reads feel like common sense once you know what to look for. We also check ourselves. Instruments overlap by design. Some scan the whole sky, others zoom in. Ground arrays catch the deepest bass notes, while space telescopes hear the high notes that air blocks. When different tools, built by different teams, tell the same story from different angles, confidence climbs. No math in your head required. For you, the rulebook is short. Color shows temperature and ingredients. Brightness shows distance when the bulb is a known type. Flicker shows size. Shadows show curve. Lenses show weight. Ripples show motion written on space. Put the clues together and our rankings make sense. A black hole merger wins the tallest spike. A gamma ray burst wins the fiercest beam. A quasar wins endurance. Dark matter wins as the organizer. Dark energy wins as the patient ruler. Different weight classes, one game. In the next step, we bring those clues down to human scale. If a person, a city, or a planet wanted to handle more power, what would that look like? How much do we already draw from our star? And how could we climb a rung without dreaming of bottling a quasar? The answers are smaller than galaxies, but big enough to change lives, and they follow the same rules that govern the sky. Bring the cosmic scoreboard down to street level. If a person, a city, or a whole planet wanted to handle more power, what would that look like day to day? The rules do not change just because the scale shrinks. Gravity gathers, fields guide, engines ignite, energy flows. Our job is to catch flows that already pass through our neighborhood and to return the leftovers gently. Start with the star that pays our bills. The sun is a steady lamp, and Earth rides inside its beam. We already sip it through rooftop panels and desert solar farms, and through the quiet work of wind, rain, and waves, each a side effect of sunlight heating air and seas. A bolder step keeps the same logic. Collect light above the clouds and beam it down as a soft microwave spotlight to compact ground stations. No smoke, no night pause, just using the river of light that is already there and guiding it where people live. Now the fire we try to bottle. Fusion. Stars fuse light atoms into heavier ones and release energy. The dream is to copy that in a controlled way. On Earth, the fuel is a thin, blazing gas. Powerful magnets shape it into a donut and keep it from touching the walls while it cooks. If we tame it, we get a tiny star on a leash that runs on fuels we can make from water and leaves very little long-lived waste. The checklist is simple to say: keep it hot enough, tight enough, and steady long enough, but hard to do. Still, the direction is clear. A compact, clean engine that echoes what the sun already does. There is a ceiling we cannot ignore: waste heat. Every watt we use becomes heat somewhere. Cities glow in infrared the way a campfire warms your hands. As usage grows, we must spread and shed that heat so climate and comfort stay steady. That is not a deal breaker, it is design. Better insulation and ventilation, cooler data centers, smarter buildings, leafy streets, and grids that move energy like blood, constant, balanced, responsive. Let us grow without cooking the room. Think bigger with a gentler image. A field of mirrors around a star, a rigid Dyson shell, is a sci-fi myth we can skip. The practical picture is a Dyson swarm, countless independent collectors on many orbits, sipping sunlight and whispering power wherever it is needed. To distant eyes, the star would look dimmer in visible light and brighter in infrared, because those collectors would glow with waste heat. That glow is how we would notice advanced neighbors. We already search the sky for such fingerprints, because even the biggest engines must shed what they cannot use. Where do cities fit in this? A city is a living grid. Rooftops harvest light, batteries smooth the day, geothermal wells hum in the background. Wires and control software shift load like a conductor, guiding sections of an orchestra. When a storm knocks one piece offline, the grid reroutes without drama. The goal is not infinite power, the goal is enough, clean and steady, with room to grow and slack to spare. Transportation follows the same script. Move people, not empty seats. Move electrons, not engines. Ships and planes sip fuels made when power is plentiful and clean sunny afternoon electricity turned into hydrogen or synthetic liquids. On land, most motion runs on direct electricity. Fewer explosions, more quiet talk. Streets get calmer as power gets smarter. There is also power in timing. The universe taught us that fast flicker marks small engines and slow changes mark big ones. For us, timing means using more when clean power is flowing and less when it is scarce. Dishwashers run on noon sun, cars charge on night wind, prices whisper that schedule to devices and devices listen. No drama, just rhythm. Place all of this on a ladder, people like to cite the Kardashev scale. Type 1 is a planet that uses the energy available on its world without wrecking it. Type 2 harvests most of its star. Type 3 taps a whole galaxy. The labels are rough, but the lesson is sharp. Before dreaming of swallowing starlight, master the art of living well on one world. Build with the flows we have: sun, wind, water, and heat from below, and do it in ways that keep the world pleasant for trees, oceans, towns, and the night sky. What about the risks we must power through? Space weather can trip grids. Hard shields and flexible systems keep the lights on. Asteroids cross Earth's orbit. A gentle push years early can shift a path. The same engines that light cities can power radar that watches the sky, and rockets that test deflection. Power is not only for comfort, it is for care. There is a softer form of power we often forget to count. Knowledge. A tiny sensor on a farm that warns of frost can save a year's work. A better map can cut a ship's fuel. A shared forecast can empty a town ahead of a storm. Every bit we learn lets us do the same work with less energy. The most ethical megawatt is the one you do not have to generate because you designed the system well. If this sounds humble next to black holes, good. We do not need a quasar's roar to thrive. We need sturdy, fair, human-scale power that borrows from the same playbook as the cosmos and returns the leftovers gently to the night. The sun's light, Earth's heat, and the quiet spin of the grid are enough to write a good story for a long time. So what is the most powerful thing in the universe for us? Here, now. It is the flow we can actually catch and steer, the sunlight that lands on rooftops, the wind that combs the hills, the warmth under our feet, and the patient know-how to weave them together. The titans we met are proof that energy is everywhere and that nature rewards good channels. Our task is not to build bigger fireworks. Our task is to lay better channels. In the final chapter, we will bring the whole tournament home. We will pick our champions one last time, not with numbers but with reasons, and close with a simple answer you can carry: a sentence for the tallest spike, a sentence for the fiercest beam, a sentence for the longest burn, and the one sentence that, for a human life, matters most. Bring the whole tournament home. We have met spikes, beams, furnaces, quiet rulers, and dark rails that guide them. Now we hand out last ribbons, then give a human answer you can carry in your pocket. Tallest spike in the shortest time, two black holes colliding. For a blink, the universe rings and more power rushes through space as ripples than all the starlight shining at once. That note is short, but nothing we have seen beats it for raw burst. Fiercest beam of light, a gamma ray burst lined up with our eyes. A dying giant drills a jet, or two tiny dense stars crash and fire a blowtorch across the cosmos. If you stand in the beam, it is a flood. Step outside it and the sky goes quiet, reminding us how much direction matters. highest power packed into the smallest space. A flaring magnetar, a city-sized star cracks, magnetic lines snap like steel cables, and a spike of high-energy light slams outward. It does not win on total output, but on intensity per spoonful of volume. It is unmatched. Longest, steadiest burn. A quasar, a supermassive black hole eats. A hot disk glows, and jets carve bubbles bigger than galaxies. The lamp stays bright for millions of years, bright enough to heat and stir the space between galaxies, and to slow the making of new stars. Greatest organizer of where energy flows, dark matter. It does not shine, but its gravity builds the cosmic web, funnels gas, and sets the stage for every engine in this story. Take away the web and the traffic of power falls apart. Patient ruler of the universe's overall motion, dark energy. It does not blaze or flare. It simply makes expansion speed up, shaping the future by gentle insistence. Over deep time, it decides which places can ever talk to each other again. Most efficient engine we can point to, a spinning black hole with a magnetized disk. Feed it slowly, and it hums. Feed it hard and it throws light and jets with record efficiency, turning falling mass into energy better than any steady process nature offers. Those are the crowns. But a fair ending should also answer the title as a sentence, not a scoreboard. So here it is, 3 ways, each one true, each one about a different kind of power. For a single instant, the most powerful thing in the universe is a black hole merger ringing space itself. For light aimed our way, the most powerful thing in the universe is a gamma-ray bursts jet. For sustained influence over the shape of the cosmos, the most powerful thing in the universe is dark energy's steady push. And now the human answer. For daily life, the most powerful thing in the universe is the flow we can catch and steer without breaking our home. Sunlight, wind, the warmth under our feet, and the shared knowledge to weave them together. A quasar's roar cannot boil your tea, the sun can. Knowledge turns a star's gift into heat, light, food, and time. Keep 2 images with you. First image, the night you step outside and the Milky Way looks like smoke. That glow is a river of distant suns along dark lanes of dust, and somewhere behind the curtains, a quiet black hole waits. The same physics that lights a quasar is sleeping in our galaxy's core. Second image, a day when the breeze pushes a line of turbines on a ridge and a panel warms a home. That is starlight, caught and used. The ink is the same, the handwriting is different. If this story has a moral, it is this. The universe does not have one champion of power. It has many, each ruling a weight class. Spike, beam, density, endurance, reach, and efficiency. Most powerful only means something when you say at what and for how long. When we add those last words, the chaos turns into a map. Maps matter because they help you act. When a headline says a burst was the brightest ever, you can place it next to your mental trophies without being fooled by scale. When a new telescope draws a shadow around a black hole, you know the shadow is not the hole. It is the shape light makes when gravity gets wild. When someone promises free energy, you can ask the only question that counts. What is the source? Where does the waste heat go? And who keeps the grid steady when the wind naps and the clouds wait? Power is not only what the sky throws. Power is also patience, design, and care. It is the choice to build channels that fit the flows we have and to return the leftovers gently. It is the discipline to measure before we boast. It is the habit of asking better questions. How big? How long? Which direction? Who benefits? Who pays? So here is the closing scene. The camera floats above Earth. Dayside, a bright patchwork of clouds. Nightside, thin threads of city light. An aurora curling green at the pole. The sun sits off-screen, steady as a drum. Far beyond, a quasar hums, a burst flickers and fades, and a pair of black holes whisper a rising note across 1 billion light-years. None of them notices us, but we notice them, and in noticing, we learn to keep our own lights bright without drowning the stars. Look up often. Think in weight classes. Catch the flow that already falls on you. And remember the answer. You can share in one breath. Instant spike, black hole merger, brightest beam, gamma ray burst, longest burn, quasar, widest reach, dark energy, best organizer, dark matter, best engine, a spinning black hole with a disk. For us, the most powerful thing is the sunlight and know-how we can use today. That is the universe's power, translated for a human life. May it leave you curious, calm, a little more at home under the sky.